I hope you joined this session in the hopes of learning something about DuckDB and having an overview of DuckDB, because this is exactly what I'm going to present in the next 20 minutes or so. So a few sentences about me. I'm a former academic. I spent a decade in academia working on databases, graph processing, and benchmarks. Now I am a developer relations advocate at DuckDB Labs. This is a small startup of 18 people based in Amsterdam, and we developed the DuckDB open source project. So what's the context for this work? Why does the world need yet another database? I think a good starting point is this tweet that was made in late October by DHH, David Heinemeier Hansen, when he said, "The fact that mainstream developer laptops now ship with 16-core 3-nanometer CPUs is one of those the premise changed fundamentals." And he argues that it is time to reconsider some fundamentals of where things run, how, and when. And of course, what he likely had in mind was Apple's announcement of the latest MacBook Pro lineup. Apple announced that you can now buy a MacBook Pro with a 16-core CPU. You can spec it up to have dozens of gigabytes of RAM, up to 128, and you can have very fast SSD storage in these machines. And this is not limited to Apple. You can get a pretty amazing laptop by basically any vendor these days. And these beefy machines mostly sit on our desks, and they are idling, running a browser tab, and maybe an instant messaging application. But DuckDB thinks it would be great to make use of this power, and therefore we built DuckDB as an analytical database system for this new era where we have powerful end-user devices, and we would like to harness that power for data processing. So DuckDB, in short, is an analytical SQL database. It was built from the ground up to be very portable and very fast. It is relatively young as far as database systems go. It's been in development for a bit longer than 5 years. It's written entirely in C++11, and it's fully open source under the very permissive MIT license. So to make DuckDB work in this new era of powerful end-user devices, we had to rethink a couple of things, and this starts at the deployment model. You see, traditionally, systems were running in a client-server setup where you had the client application running on your local computer or workstation. Here we have a client application implemented in Python, and then we had the database server running somewhere, typically on a strong, big iron machine. It can be an on-premises cluster, or it can be in the cloud, but it must be a big machine. And it must be also an expensive database, because it's usually something you have to pay for, then you have to configure it, maybe hire a DBA to run it. It's all quite complicated to set up. Then on the client side, you configure something like a connection string and authenticate your user. And even once you have done all this, we have a huge problem. We have the client protocol in the middle, which is this tiny, narrow straw where we have to send the queries through and receive the data back. And this is a major bottleneck as far as performance goes, and it severely hinders the usability of this setup for analytical data workloads. Of course, if these laptops are so amazing now, we can just take the database and bring it on the laptop, right? Well, not so simple. These databases are big, unwieldy pieces of software. Chances are that they will not run on macOS, and you need to run them in a container to have any reasonable chance of success. Then you need to configure that, adjust the ports, and so on. Sure enough, the configuration is a bit simpler, but you will very much end up with the same problem. You have a client protocol where you have the data pushed back and forth along this tiny protocol that was not really optimized for gigabytes of data. So DuckDB's idea is to take this and do it to the extreme where the database server lives in the client application. So the database server is taken into the client, which makes a lot of the things completely trivial. For example, you no longer have to configure anything, you don't have to authenticate, and the client protocol is gone. And you can just start saying duckdb.sql and work against an in-memory database. Of course, persistent is not a bad thing. So you can say that I want to connect to a database file, and then you can run that database file and run queries on that. So we have a single file format for DuckDB that contains your entire database, including all the tables. And now you may get a sense of deja vu because, yeah, this is an embedded database that runs in the client process, and it has a single file format. You have seen this already, right? There is SQLite, the most popular database that's the most widely deployed on Earth. Well, true, SQLite was a major inspiration for DuckDB, but DuckDB is a bit different. If you think about database systems along two axes, in-process versus client-server in terms of their deployment model, and transactional versus analytical in terms of their target workload, you can see that SQLite targets transactional workloads where you only access a couple of rows in each query, whereas DuckDB targets analytical workloads like data warehouse systems like Vertica or big cloud data warehouses like Snowflake. And this makes DuckDB quite unique in its category. Of course, for DuckDB to be usable, we wanted it to be very portable. And this means that you should be able to get DuckDB up and running in less than 15 seconds on most popular platforms. And I really do mean less than 15 seconds. This should include typing the commands, downloading the packages, waiting for the installation to complete, and launching it. And I have created two recordings for this. One is macOS and the most popular DuckDB platform, Python, and the other is on Windows. You can see that you can install DuckDB indeed by just saying pip install DuckDB. It will fetch it from PyPI. Then you start a Python process, import it, and you start firing queries like select42 right away. And the whole thing took 12 seconds. It's a similar story on Windows. You say install.packages in your RStudio window. It grabs this tiny binary, which is just 8 megabytes. You import it, and you can start working with DuckDB. So this is, of course, very different from the experience of setting up an actual standalone client-server relational database system on your laptop, which can take hours to work. DuckDB is not limited to R and Python. We support Julia, Node, JavaScript, Go, Rust, and so on. And we support all major operating systems and all major computer architectures, including x86 and ARM. So why is DuckDB so fast? One of the guiding design principles in DuckDB's creation was that it has 0 external dependencies, because we found that that makes portability very difficult. Of course, we did not reinvent things like regular expression matching, so we vendor these libraries into the code base. But at the end of the day, we have a pure C++ code base that has no linked dependencies. So wherever you have a C++11 compiler, you can run DuckDB there. And we also get small binary packages as an added benefit. An extreme of this is the WebAssembly implementation of DuckDB. So DuckDB can be compiled to the WebAssembly platform, and then it runs within your browser. So you can open a browser tab, and DuckDB loads as a WASM application, and everything within DuckDB runs in your browser without ever talking to the remote server. So this is, of course, something that opens up very many interesting use cases. So DuckDB is fast to install, but is it actually fast as a system? Well, being fast starts at being able to get the data in the system quickly. And for this, I have a bunch of data points. I used a sample social network dataset and loaded it into DuckDB using the laptop that I'm presenting from. I have 3 categories, small, medium, and large. And you can see that they range from 7 to 73 gigabytes. And the load time is pretty good. You can see that DuckDB loads the data at more than 1 gigabyte per second, which includes reading the CSV, parsing it, and writing it back to a DuckDB database. The DuckDB database that we create is quite compact. DuckDB achieves roughly a 3 times compression over the CSV data that is sitting as a raw uncompressed CSV on disk. So it's demo time. Let's see how DuckDB works in practice. So we have a Jupyter Notebook running here. And I was ambitious, and I wanted to show you the large data set, the 73 gigabyte data set that takes about a minute to load. So I will first start the loading process, and then I will walk you around to explain what is happening. So this is the size.l directory. And the size.l directory has a bunch of tables like comment. So comment is a bunch of CSV files generated by Spark. You can see from the file format that there are many chunks of this. So let's open one. Jupyter is struggling a bit, but eventually it will show us a preview of this. And we can see that it doesn't look right because it didn't guess the delimiter correctly. It thinks it's separated by a comma, but it should be a pipe. But once we give this hint to Jupyter, it renders the table, and it's a fairly usual table that you would see as a data engineer or data scientist. We have a timestamp column for when the comment was created. We have int64 IDs, IP addresses, browsers, content, some shorter, some longer, and some information on who created that post and where it was created. In the configuration side, it's all very simple. We just import DuckDB, import pandas, connect to a persistent database, set up a few things to make sure everything is looking nice, and then we select this magic that allows us to run SQL queries. And it has already finished, so it took like 74 seconds. And what you can observe is that it loaded more than 500 million rows in that amount of time. So it crunched through all those CSVs. And what's even more interesting is that we never had to specify anything like what is the separator or what are the types of the individual columns. So it would be a good idea to check whether DuckDB indeed managed to find this information and managed to deduce this. We have a command called describe in DuckDB SQL dialect. And if I run this, it will give me back a nice little table that shows that it indeed correctly assumed the schema. So we have the creation date, which is a timestamp. We have an int64 ID. We have various varchar character fields for the text data fields, and a bunch of integers for length and other IDs. So DuckDB did this all without us having to tell it what the data format is. This makes it very quick from a development perspective to get data into DuckDB because the CSV reader does most of the heavy lifting for you. If you want to peek into the data, we can, of course, just do a select star query. This runs instantly, and it shows us what we have already seen in the CSV format, but in a nicer table format in the notebook. Now, let's see a couple of queries starting with aggregation. For example, we would be curious how long the comments are in the data set. So remember, these are more than 500 million rows, so we have to go through all of them and calculate the average. DuckDB takes very quick work of this. It takes like 250 milliseconds, and it immediately gives us the answer that is 33.26 for the average comment length. Maybe this was too simple, so let's do something more involved. Let's see the number of comments made in each month. So we extract the month from the creation date column, and then we count the number of comments that were made. This takes about 1 second, and we can show that this is the result as a DuckDB table from the month of January to December. Now, this is a bit difficult to interpret, so we can very quickly invoke the .dataframe function and turn this into a Python data frame, then use Pandas's plotting library, and then get a very nice bar chart that visualizes. And now it's obvious that we have an increasing curve that has more and more comments until October, and then maybe there's a cutoff in November where the data collection stopped. So that would explain this shape. All right, let's move on to the join operations. If you know about relational database systems, you know that joins are typically heavy-hitting and complex operations. So let's try to work with this data further and establish the number of comments per each country. For this, we need to do a join operation that joins the location country ID on the place table. DuckDB also does this fairly quickly. It's just 1.25 seconds. And unsurprisingly, most comments come from the most populated countries, namely China and India. Let's do an even heavier join. So here we have two joins. We have the comment table, then we go to the country, then we go to the continent, and we count the distinct authors, which is a complex aggregation, per each continent. DuckDB also finishes this in about 11 seconds, and it gives us a detailed breakdown of how many individual authors we had per continent per month. This is, again, not that easy to see through. So we can use something that's very popular among data science users, namely the pivot operation that turns a long table into a wide table. DuckDB has a very nice syntax for this. We just say you want to pivot on the continent using the number of authors. And this is an instant operation, like 28 milliseconds. And we pivoted the data into this wide form. And similarly to what we did before, we can pipe it into a results table. And maybe we want a nicer plot now, so we will invoke seaborn and create a heat map that shows that as the month progresses on the vertical axis, we get more and more individual commenters as we would expect. And we also have Asia as a more populated place, having more comments, having a deeper color on the heat map. All right, so we have a data frame now. That's great, because then we can use our pandas knowledge. Many people are a lot more comfortable in pandas than they are in SQL. So maybe they want to do something like, let's do the average quarterly number of individual authors per continent. And we can formulate this succinctly in pandas and return this as a quarterly underscore average field. Now, the interesting thing is that getting this back to a normal database system would usually require some work. But DuckDB has an interesting mechanism called replacement scans. And a replacement scan is essentially DuckDB's mechanism to say, well, if in the from clause I see something which is not a DuckDB table, then I will look around in the Python environment and try to get that there as a data frame. So if you say select star from this, it will read the pandas data frame directly without copying, and it can do further operations on it like this filtering and return the results. So it's very easy to go back and forth between pandas and DuckDB. And this is something I would wholeheartedly recommend to pandas users. If you have a pandas script, don't ditch the entire thing, but maybe try to gradually integrate DuckDB into the points where pandas is maybe a bit slower than you would like it to be. All right, finally, we did a lot of pivoting. Let's do an unpivot. It's very easy to use unpivot and just say we want to unpivot this table back to a long table based on every column but the quarter. And then the continent becomes a new column instead of being headers, and we see the authors there. So pivoting and unpivoting also work very neatly back and forth. All right, what allows this speed from DuckDB? So database systems come in two particular kinds. We have row-based and column-based storage. In row-based storage, we store the tuples together. And in column-based storage, we store the cells that belong to a column together. Now, this has a profound effect on execution too. In a row-based model, we usually have a tuple at a time processing, where we process the data row by row, which is not ideal because we have to read all the attributes, even the ones that we do not use in the query. And it causes a lot of context switch, which is not really playing nicely with modern CPU architecture. Column at a time is a better model if we do analytics, because if we want to do something like an aggregate of the length over time, then we only need to get the length and the time. The problem is these columns are huge. In our previous example, they had more than 500 million rows. So if we do column at a time processing for large data sets, we will just crash and run out of memory. So a third approach that we have for execution is vectorized, which is kind of a Goldilocks approach. We have chunks of these columns. So we have in DuckDB chunks of 2048 rows. And we do the processing on those, which gives us a lot of the benefit of being friendly to the CPU, but also spares us from running out of memory. And the way DuckDB utilizes this vectorized execution model is that it takes row groups. Now we see two row groups of 4 rows on the left, and it parallelizes along these row groups. So the first two go to thread 1, and the next two go to thread 2. And then these vectors are pushed through the CPU core as the processing happens. And the nice thing is that because we have roughly 2,000 tuples in a vector, these fit neatly in the L1 cache, which is now 32 to 128 kilobytes, which makes it very cache friendly, very pipelining friendly, and in general, it allows us to skip most of the random accesses. So this is great because it gives a very fast processing, especially that modern C++ compilers can auto-vectorize code using single instruction, multiple data instructions. So this is a very efficient way of crunching through data with big bulky operations like aggregations and joins. Regarding the indexing, DuckDB uses something quite clever. It's called the zone maps, which means that we create minimum, maximum indexes for each row group. For example, here, we index time and length on this slide, and we show that the minimum of the time for the first row group is the 7th of December, and the maximum is the 10th of December. And this is very useful, especially if your data is ordered, because if I ask something like what happened on this day, the 13th of December, then we can just go through these tiny min-max indexes, and then we can establish that it's only the second row group that we need to touch. So we do not have to touch any other row group, and we do not have to touch any of the other columns that we need, which makes the data access a lot more limited, allowing for very fast queries. DuckDB also has very nice support for larger than memory execution, also known as out-of-core execution. Here we have a couple of plots with the popular TPCH benchmark. And these plots are not that easy to read, so I will walk you through them. On the x-axis, we have the memory limit. So it's the decreasing memory limit from 30 gigabytes to 0 gigabyte. And on the y-axis, we have the execution time. And we can see that it doesn't really matter whether you have 20, 25, or 30 gigabytes of memory. Most queries do not even need that. But when you go lower, when you go below 10 gigabytes, the queries start to get a bit slower. But DuckDB does this in a very graceful way. And in most of the cases, it's able to finish with maybe a penalty of 2 to 2.5x. And sometimes there is a crash, but it's only when it's very limited in terms of memory, and it's a very complex join-heavy query. So some of the queries are not able to finish with only 1 or 2 gigabytes of memory, but most queries have no problem completing, even though this is a 100 gigabyte data set. All right, on to one of the most exciting things about DuckDB, extensions. DuckDB has a very powerful extension mechanism because we wanted to keep the core lean and portable. And to this end, we have an extension mechanism that allows you to define new types and functions, new data formats, even new operators and SQL syntax. And many of DuckDB's core features are implemented as extensions. HTTP support, JSON support, and Parquet are all DuckDB extensions. So we follow the eat your own dog food principle with the extension mechanism. And the extensions do not just exist in isolation. They can even collaborate in a sense. For example, if you run this query that gets the average price for the Microsoft stock from our prices.parquet file, it's not going to download the Parquet file from the internet, then do the aggregation on it after extracting the price column. It will use the Parquet metadata to seek to the required data that is the price column, and it will fetch only that from the server, again, greatly reducing the I/O required to complete the query. Our extension mechanism also works in the WebAssembly version of DuckDB. So you can install something like the spatial extension, you can load it, then you can get data into it from github.com and do calculations like counting the number of taxi stands per borough using the New York taxi dataset. Okay, so what do people use DuckDB for? Well, to put it bluntly, many people just use it to save money. DuckDB is free, it's easy to get set up with, and it's relatively fast. So you can replace big parts of your data warehouse or cluster compute jobs with just a single node that runs DuckDB, or you can just run computations on your laptop, and that can also replace quite a lot of computations that people were previously running on servers. DuckDB is often deployed as a building block, so there are lots of use cases when people just import DuckDB, convert from Parquet to a CSV, and then leave it at that. So that's a very simple way to get started with DuckDB. And we noticed that teachers like DuckDB because it's an easy to install system, it's open, standards compliant, and the students don't have to bother with configuration, and you don't have to hire a DBA to keep the cluster running during the weekends. Of course, DuckDB is not a solve-all system. Even though we support concurrency control and we have transactions and recovery, DuckDB is not a great fit if you have write-heavy workloads. You can work with multiple processes using the same DuckDB database, but then you are required to only read that database due to caching reasons. So if you want to work with a read-write mode, then DuckDB is limited to a single writer. Another limitation of DuckDB is that it doesn't support distributed execution. It only supports single node execution. That said, we did a lot of work to make it scale up, so you can run DuckDB on machines with 1 or 4 terabytes of RAM. These are available for everyone in clouds like EC2. And this allows you to scale for terabytes of data. So we see people use this model where they store the data in an S3 bucket, grab it, run a short burst of workload, and then they are done with it. So the DuckDB landscape, we are currently at v0.9. Next year, we have one more version, v0.10, before we go for the big one, which is v1.0. v1.0 is expected by many people, I think, because it will finally introduce a stable storage format, along with stability and maturity improvements, and the usual performance optimizations that we have. Regarding the organizations around DuckDB, Jordan Tigani, the CEO of MotherDuck, had an excellent talk yesterday where he explained how DuckDB, DuckDB Labs, and MotherDuck work together. MotherDuck is a cloud-based version of DuckDB where you can work in unison with a local DuckDB. You can run hybrid queries where part of the query is local and part of the query runs in the cloud. So to wrap up, I think DuckDB is a funky system because it's a good old school open source project where you can work with CLI, work offline, and you have a standards compliant SQL that doesn't lock you in. It's very fast, and it has support for many of the popular data formats. So if you're interested, give DuckDB a spin. It's pre-installed in Google Colab. We have the WebAssembly shell for you to play with. And if you're interested, we would love to hear more. Join our Discord or reach out on our socials.